of this great conference. I am Irene Giardina, and I will be the chairwoman for this last session. So our first speaker is Matteo Marsili, who will talk us about the Jij equal plus minus J easy learning machine.
Okay, thank you very much. So, yes, first of all, I would like to thank the organizers of this really amazing conference. Actually, my gratitude extends far beyond I mean, 35 years ago, I was starting learning physics in this very lecture room. So, and then since then, I benefited quite a lot from interacting with all this community. So, I'm really happy to be here. So, what I will discuss today is a particular work that I did with Odilon Duranton, which is a master student of École Normale Supérieure. But this builds on ideas that I've been developing with other people listed here on a particular ideal limit of learning machines. So the problem is the one of learning, and it's a problem which is very, deals with a lot of systems in life sciences, so since when we are born. And as physicists, we have this idea that essentially we see the world and we learn, classify stimuli out there, and somehow, somewhere in our brain, we create a free energy landscapes where essentially the minima corresponds to the most frequent things that we see around and the most relevant things that we see around. Now, the great thing about neural networks and machine learning is that you can really have statistical mechanical models for which you can pose this question in a very disciplined manner. And so you can make this picture a little bit more precise. And actually, there are many people in this room that have studied this problem. And generally, the idea is that you see statistical inference as inverse statistical mechanics, as the inverse problem of statistical mechanics. So in statistical mechanics, you start from an Hamiltonian, and you want to get to the distribution of over the space of configurations. And you know that this is given by the maximum entropy. If you maximize the entropy at a given energy, then this gives you the right answer, and in equilibrium. And now, in machine learning, you have you start from some data. So in principle, the distribution is given by the data. And then these machines, you have a learning algorithm, a learning dynamics that I will not discuss. But in the end, you converge to a particular system whose internal representation has some particular energy landscape that you would like to understand. And essentially, you would like to understand whether this landscape is similar to a spin glass, Hopfield model, or whatever other type of model. And there are many people, as I told you, that have studied this problem in this room, so the list would be just too long. And so the question is, of course, when you do this thing, this energy landscape is obtained by minimizing an error or maximizing likelihood. So you have a goal function that depends on what you want to do, and that is the result. But there is no not a general principle like this one that tells you what are the statistical properties of this energy landscape. The other issue, which I think is important, is that when you do this learning, your aim at studying data which have a very rich structure. So they are not just random noise. It's not just noise. Okay, it's really there is a lot of structure. This is actually why you build this machine, because you want to extract this structure and to give it a particular specific representation. And what you want to do is to extract features such that essentially you can distinguish the inputs according to the values of these features on the different data points. Okay, so this is what makes this problem very specific. So I will first argue that there is I mean, I will propose a principle by which you can derive the energy in an ideal setting, and then I will describe what happens when you apply this principle to a specific case, which is the Ising model. So in order to understand what type of models turn out to be efficient, optimal learning machines in this case. Okay, so so here is a little bit of the setting. As I told you, I'm studying the statistics of the states in the internal representation of one of these machines in a very general setting. So this is something that you can obtain, for example, in the extracted Boltzmann machine if you just marginalize over the visible layers and over the other layers in deeper architectures. So if you have a state, you can compute what is this marginal distribution. You take minus the log, and this is my variable, my energy, which is just the coding cost. How many bits are encoded in this word S. If you average these over the distribution of the states, then you get the entropy. Now the entropy here becomes the average of the energy. And this is the average coding cost, which I will call resolution. And to large, I mean, the idea is that essentially this is a quantity which can be tuned by choosing, say, the number of hidden units, for example. So it's a user-defined quantity. Instead, the important player that I will I will try to argue, is this relevance, which is the entropy of the energy as a random variable. So what you should do is compute the probability distribution or to observe an energy E, which is the degeneracy of energy levels times e to the minus E, and then do P of E log P of E sum over E. And the point that I want to make is that this is really what plays an important role in learning, because essentially what I argue is, I will try to convince you of, is that optimal learning machines are those that maximize this relevance at a given resolution. So the idea is that if this is, yeah?
Can you go back one slide? Why H still depends on S and it's defined as the sum of all the states of S?
Sorry? No, okay, so it's a way, so you should think S, this is a functional of S as a random variable. Is this the question?
But you sum overall.
Yes, so
Okay, so H depends on the distribution of S.
yeah, it's a function. So S is a random variable, and
P of
yeah.
S, that would be H of
Yeah, it's h of p of s, yes. Sorry, it's just notation. Okay, so this is the amount of bits that you have in your representation, and what I'm going to argue is that this part is noise. So all the states that have the same energy are indistinguishable from noise, and whereas the signal is actually is this part, is the entropy of the energy. And actually, you can argue that these many bits are how many bits you learn about the generative process of how many bits your representation contains on the generative process of the data. But okay.
Can you explain again the equation?
This one? So this one is just you maximize, you find the Hamiltonian within a certain class of Hamiltonians, such that this object here that I defined previously is maximal at this resolution, at this average energy. Okay, it's yeah. So this there's a prediction that say if you just maximize this over, so this depends on the distribution of energy density or energy levels. If you just maximize this over possible functions of possible degeneracies of the energy, then you find that the solution of this problem generally has exponential energy, the degeneracy of energy levels is exponential, which essentially, if you project it on a finite sample, it tells you that the number of times that you see a particular outcome should be power law. And this is what has been called statistical criticality. So before showing you that this is actually what has been observed in many of these learning machines, let me try to give you an intuition of why, where this exponential distribution of energy level comes from. So the idea is that I'm going to think about, I mean, this is not my particular view, this is a view that I learned from Tali Tishby when he was giving lectures at ICTP. So you think at your inputs as typical draws from some distribution. These are typical sample from a very high dimensional distribution. And so you can think that generally this distribution satisfies a sort of asymptotic equipartition property in the sense that more or less all the inputs that you are going to see are equiprobable. Okay, so this makes a lot of sense. And what we are interested in is to characterize this typical set of inputs. And the way we do that is to divide or say tessellate this set with typical sets of inputs conditional on a particular state of the machine. Okay? So for each state you have a different typical set, and this is the way in which you want to represent the typical inputs of your machine. So I mean, this would be cats, this would be dogs, these airplanes, etc., etc. Okay? Yes?
I don't see very well the equation.
Oh, sorry. So this is just the typical set. So typical set are the sets for which minus the log of the probability of the points is within epsilon of the entropy. Okay? And you can do this for the distribution of x and for the conditional distribution of x given S. Now, you can probably not even see this, but essentially this tells you that for any point, if I take a point here, its probability will be the probability of getting this x given S times the probability of S. And this tells you, if you take the log, that the energy of this blob here, so which is minus the log of the probability of P of S, must be the mutual information between X and S. Well, it's not the mutual information, it's just the difference between this entropy. Here, S is not a random variable. Now, the second bit is that if you now combine this, if you take all the sets which have the same energy and pick any X in these sets, then you should also have that the probability of this point at a particular energy should be decomposable as the probability of X given S times the probability of S given E. Okay? Now, the probability of S given E is just 1 over the number of states that you have at the energy E. Okay? And if you look at this equation for all energies that you observe with a probability, with a finite probability, then what you get is essentially you get you get an exponential distribution of energies. Okay. Now, this of course implies that this of course implies fixes also the resolution. If you want to scan different values of the resolution, what you have to do is to use large deviation theory. And so essentially that includes another factor nu times E in this exponent. And so this is how you get this exponential distribution. Now, this is so general that it also applies to physical systems. The issue is that in physical system you see only essentially one value of the energy, because that's the equivalence between ensembles. Now, what happens in optimal learning machines is that essentially the range of the energies that you see is very broad. So these blobs have a broad distribution of log sizes. And this corresponds to the fact that in the end you want your energy to be like a linear combination of the sufficient statistics, which are the features in your data. And the idea is that you want to find features which have a broad variation across the data, so that your energy will also have a variation that is as broad as possible. Okay, so this is the idea. I hope I convinced you. But if you accept this idea, then you can study what are the properties of systems that have this maximal relevance, that maximize, or that have this exponential distribution of energies. And what you find is that you find a relation between the energy and the entropy, which is the noise level, which is the log of, would be the Boltzmann entropy, which instead of being concave, as in statistical mechanics, now is convex. And this has a clear interpretation in terms of what happens when you go from a certain representation to a representation which is a little bit more compressed. So if you decrease your resolution by 1 bit, the relevance or this, the noise will decrease by by nu bits, which means that when nu is larger than 1, you're essentially in the regime of noisy, so your resolution is still noisy in the sense that you can still compress and eliminate more noise. At this point, instead, you are at a very particular point where beyond that point you have to sacrifice important bits. Okay? Okay, so this is what comes out of this prescription. And so this statistical critical, this signature of this exponential distribution have been observed both by us and by others in several systems that that are, say, efficient learning machines like restricted Boltzmann machine, deep neural networks, etc. And also, well, you can argue that also living system can be thought of as efficient or optimal learning machines. And so, so this gives you an idea of why you see these features also in other systems. Okay, so there is another principle that we found is, at least in a particular system, we find that a property that you expect in an efficient representation is that you would like to be invariant with respect to the resolution of the input. And this is something that, at least in this particular system, we found it be only true when you have exponential distribution of energy levels. Okay, so if there are no questions, then I would just, what I would like to do in the next 4 minutes, is to say, okay, let's pick a particular architecture, the Ising model, and let's look how does the Jij that maximize this entropy at a particular, this relevance, at a particular resolution look like. Okay, so we know that the entropy generally scales is proportional to n, so I will rescale the entropy by n log 2 so that this Hs goes from 0 to 1. And also the number of different energy levels that you can see is almost n squared, because there are n squared terms here, and everything is discrete. So this, I can rescale this object here also by log n. So I get a number which goes from 0 to 2. Okay, so I will first describe a simple case just to set the stage, then what happens for small system, then for some large architecture. So one thing that one has to take into account is that the energy density on which this goal function, this entropy, the degeneracy, is invariant under gauge transformation. And this, I think, is interesting because essentially since you are stretching the energy scale a lot, then it means that when you make a gauge transformation on one of these efficient machines, then you find completely different systems, so that the spaces should be disconnected if you look in the space of J in this efficient learning machine, whereas probably this is not true if you just take random Jij. But say, okay, so this is what happens with the mean field ferromagnet. Ising ferromagnet. So essentially the bottom line is that you get that the entropy, this relevance, this scale relevance, goes to 1/2 for all values of J, but only at the critical point you get 3/2. And this is what you can also get by an explicit calculation. So the convergence is also very slow. If you look at small systems, what you find is that the optimal learning machines are, they have few negative Jijs, and they are distributed in a very non-homogeneous manner. So in particular, what you find is that the value of the maximal value of this relevance that you achieve is much larger than what you get in the ferromagnet. And what you see is also that the distribution of energy levels, the degeneracy, is approximately exponential, and it's much denser than for the ferromagnet. Okay, so motivated by this, we studied some heterogeneous systems. One of them, just two, so I will be very short. So one is the star model, where you pick one spin and you connect it to L other spins with a negative interaction. All the other interactions are positive. So the peculiar properties of this system is that if you take n large enough, the degeneracy of energy levels becomes a space filling curve. And if you compute, so it means that you can cover essentially n squared values of the energy in this way. And if you compute, and this reflecting the fact that if you compute the value of this relevance, it's higher than in the ferromagnet, although, of course, this is a correction of order 1 over n, so the thermodynamics of this system should be the same as the thermodynamics of the ferromagnet. So this is interesting because it tells you that not necessarily true that thermodynamics tell you the whole story of, it may not tell you the whole story of learning machines. The final slide is about another model, which is a recursive model. So now this is a model where on a lower triangular part of the matrix J, we take negative signs. And this can be implemented in a recursive way. And in this way, you get also a very much larger values of these relevance, which are larger than 1. And also, it looks like you get a better convergence, and you don't get the same feature of having a convergence to different value as n goes large. Although we cannot do very large n here. Okay, so this is the summary. So the first thing, I tried to share this conviction that these optimal learning machines is sort of a scheme that allows you to pose a lot of questions in learning without having to deal with the explicit data, I mean, in a data-independent manner. And that they can, so the prediction of this exponential distribution can be checked on learning machines on this, on specific architectures. And also, what we have done is to study these optimal learning machines on a specific architecture of Ising model to understand what is the nature of these systems. They are very non-homogeneous, and their specific property may not be accessible to thermodynamics, but they have a capacity which grows faster than in critical models. Okay, so thank you very much.
Are there any questions? Light. I have one question. I mean, is there any kind of possible development in terms of dynamical measures? I mean, when you have data that evolve dynamically and you might want to find some scheme that learns in time.
So there are machines like recurrent neural networks that are used to study dynamical systems, but they have a bulk, a hidden layer. And again, you can ask yourself, is the hidden layer, what is the distribution of energies, this hidden layer? Of course, that will be like a Markov system, so you have to study the invariant measure and et cetera, but you can
do that exactly with the same criterion, but with the transition probability instead than probability itself, I guess. Okay. Okay, thank you.